that data. So I guess the two main types of supervised learning that we're going to get into is in regression and classification tasks. So regression tasks are up top. I'm not sure if you guys can see my mouse pointer. Yeah, but this is the regression task. So basically, you're able to take in numerical inputs and output numerical outputs. So for example, let's say you wanted to predict the salary of someone. You could use a regression model to take in, let's say, or in this case, they said the hours studied. So let's say someone studied for this hour and they got this score. And generally, the model we're going to be using is linear regression, which is the process of finding the line of best fit for a function. For classification tasks, you want to take a bunch of data and try to, allocate it to a certain group. So in this case, we've showed a bunch of fruits, and the machine learning model can classify the different fruits. Unsupervised learning, however, is unlabeled data. So in supervised learning, we're given both the inputs and the outputs when training. But in unsupervised learning, we don't know the actual answer during the training phase. So what they have to do instead is basically try to find connections within the data and group things together. And the last is reinforcement learning, which is basically a reward or punishment-based approach to machine learning, where something has a certain goal in mind and it'll do whatever it can to try to achieve that goal. So we're going to actually watch a video by OpenAI, the developers of ChatGPT, DALL-E, etc. And they kind of show a great visualization of how reinforcement learning actually works.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observed, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other as well as past versions of themselves using an algorithm called self-play. Co-evolution and competition on Earth led to the only generally intelligent species known to date, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction. We hope that with a much larger and more diverse environment, truly complex and intelligent agents will one day emerge.
So I hope that video kind of gave you an idea of the applications of reinforcement learning and how powerful it is. So for this course, we're going to mainly be focusing specifically on the process of supervised learning due to the time constraint that we have. But if you guys do end up getting interested, it's honestly great to look into unsupervised and reinforcement learning. So here's some of the training vocabulary that I might mention throughout the course. So I guess loss is how you calculate the error margin. So models, when they're training, they make predictions on training data. And what the loss function does is basically puts the error in a numerical value, and it can be used in the process of gradient descent. So gradient descent is the process of mitigating the loss at each stage of the machine learning training process. So in a mathematical term, it's basically calculating the derivative of each weight. So if you remember from the original definition of machine learning, we talked about how there were weights and parameters. So it'll derive each weight with respect to the loss and modify the weight respectively to try to mitigate the amount of loss that the model has. And then in actual training, there's two key terms, the batch size and the epochs. So one epoch is basically the amount of time that it takes the machine learning model to have looked at all of the training data at least once. So machine learning algorithms actually need to look at the full data set many times to actually optimize the accuracy. But within these epochs, we use batch sizes. So let's say you use a massive data set, which is very common in machine learning, of 50,000 pictures. Instead of passing all 50,000 pictures into the machine learning model at once, we split it into batches of maybe, let's say, 64 or 128. And then at each of those points, it'll update the weights as well. So I did mention that, we need to run for many epochs, but how many epochs is the right amount? And that's where fitting comes into play. So there's three main types of fitting: underfitting, appropriate fitting, and overfitting. And we aim for appropriate fitting. So underfitting is where you haven't trained for enough epochs, or the model hasn't seen the data enough times. So the pattern in the data is not yet found. So you can see in this example, there's some curvature in the groups generally, but we're seeing that it found a linear relationship, and that's why it's gotten so many misclassifications. Now, appropriate fitting is the ideal epoch count that we strive for. It's very hard to get it on the dot, but we strive to get close to this point. And at this point, the algorithm is generalized to the problem. It's expected to perform well on new unseen data. So you can see it's got the general idea of the data down, and if we were to give a new point, it would be able to properly classify it in the right group. Now, overfitting is where you've trained for too many epochs, and the machine learning model has now just basically memorized the training data, and it's no longer generalizable. So when it gets a new data point, it's not going to be able to classify properly. So we're going to get started with some of the data handling, and we're going to start with NumPy. So NumPy is a base package in Python, which we're going to be able to play around with in just a second here. And many of the machine learning libraries are built upon NumPy, including scikit-learn, TensorFlow, PyTorch. We're going to be using scikit-learn framework for our purposes here. And the main use case of NumPy are the NumPy arrays that it comes with. So I guess we can get started by importing NumPy just for now. So what I want you guys all to do is head over to kaggle.com. And this is like a massive data science platform where you can create notebooks and find lots of data sets. So I want you to come here and you can register for an account. And then once you're registered for an account, just go ahead and drop a message in your corresponding like colored chat, team class chat. And then when I see that enough people have done it, we can move on. I think some people are finishing up now. I guess I'll give about maybe 3-4 more minutes for everyone to make their account. Okay. So I'm just gonna move on now. You can go ahead and create. You're gonna see this button called Create. So just click Create and click New Notebook. And what it's gonna do is it's gonna load up a Cloud Python notebook. So far, what you guys have been working with are .py files or .py files, which are just Python files. But these are Python notebooks. And what they allow you to do is they allow you to run cells of code instead of having to run the whole script. And that's really, really useful in machine learning because often these massive machine learning models take hours and hours to train. And you don't want to be having to rerun that hour and hour of training for every small modification to your code you want to make. So instead, you split up your code into cells and run specific cells more times than specific cells, maybe just once. So it's gonna when you create your own notebook, you can title it. So I'm just gonna call it CS1 Day 8 Introduction to Machine Learning. And then you can go ahead and delete this. So this is basically they just give you some default text. Just go ahead and delete all of that. And then what you can do, I can just do this, I guess. What you can do is just to import NumPy as NP. And the good thing is all these sorts of libraries are pre-installed on Kaggle as it's a data science platform. So if you do this and just run it, you're going to have it imported. So what this line of code does is it imports the NumPy framework using import NumPy. And then the as NP is kind of just a very common convention. And it just allows you to not have to type NumPy dot for every functionality you want to use. And I guess it'll take a second for your kernel to start, and then you can turn your attention to the slides for a second in the meantime. So what are NumPy arrays? I did say that they're the fundamental aspect of NumPy. Well, NumPy arrays are similar to lists in Python, but they allow us to create multidimensional arrays that have a lot of functionality. So one of the key applications of multidimensional arrays is image data processing. So you might think of images as a 2D data type with just the width and the height with the pixels. But in addition to the height and width of the images, they actually hold 3 channel values, which represent the intensity of red, intensity of green, and intensity of blue on a scale of 0 to 255, which comprehensively make one image. And this is commonly known as the RGB format. So you can kind of think about these multidimensional arrays as in lists, like lists within lists, but they just have a lot more functionality and functions in NumPy. So a 1D array is sort of like your just standard list, the shape of 4. And then a 2D array is going to be like a list within a list, and a 3D array will be a list within a list with lists inside. And you can see the shapes here. And the good thing about NumPy is we're able to modify these shapes. So what makes NumPy arrays special, and why don't we just use these lists within lists if I can just say that they're the same thing, right? So there are similarities in terms of the data structure. We're able to store multiple pieces of information in one variable. And it allows us to index as well, where we're able to access different points using the same indexing techniques. Now, NumPy allows for arithmetic operations within NumPy arrays. And one of the key parts of it is that it takes less memory and it's faster. So in the field of machine learning, like I said, these types of models that are huge, with lots of data, take so long to train. And if we're passing in lists, that time takes even more. So if we're able to use less memory and have it be faster, we can speed up the training process a lot. Now, one potential drawback is that it only takes one type of data. So you might remember when we were looking into lists, right? We were able to have, let's say, 1 as an integer and then 2.0 as a float, and then Bob as a string, all in one list. But NumPy will throw an error if you try to put multiple types of data in one array. But for the purposes of machine learning, you're going to have to encode all values to numbers eventually before it's passed into a statistical model. So in our case, it's going to be fine. It also allows us to reshape multidimensional arrays, which we'll look into in a second. So here's some of the basic functions, and I think I'll just show you them in action on the Kaggle notebook. So the first thing we'll do is we'll create our first NumPy array. So let's just say array equals np dot array, and then in here you can put in what you would do for like a standard list. So I'm just going to put 1, 2, 3, 4. And if I run that code and I look at it, so actually one thing I'll go over. So for a notebook, you see how I'm making these new cells when I want to run something separately. And then this is also like similar to the idle, where I don't have to say print array. I can just type array and it'll show me what it is. So it's an array type with inside it has 1, 2, 3, 4. And like I said, you can index it similar to how you do with regular lists. So if I say list of 0, it's going to return 1, just like this. Or if I put list of 3, I'm going to get 4 back. Now, what else can we do, right? So like I said, we can reshape these arrays. So if I do array equals numpy.reshape the array, array.reshape, and I put in 2, 2. So I want an array that's now of 2 by 2 instead of 1 by 4. And I run this code. If I look at my array now, I can see that I have a 2-dimensional array, or a list within a list. So I've got this list, which has the 2 lists inside. One of them has 1, 2, and one of them has 3, 4. And you can't do this in regular lists. You can't take a list that's originally one dimension, and just expand it to have 2 dimensions like NumPy allows you to. And similarly, we can index, so we can say array of 0. So now array of 0 is actually going to be the first list. So it'll be just 1 and 2. But if I want to access, let's say, the 1, I would just do 0, 0. If I wanted to access the 4, I would have to grab the second element of the second list. So I have to go 1 and then 1 to access that. And then the last one we'll go over, which we'll see again when we're working on our first machine learning model, is numpy.arrange. So this will basically just, like the name suggests, it'll basically create a numpy array in a range. So if I say range array equals numpy.arrange, and let's say I go from 1 to 11 by 1s. What this will do, I'll have to run it. Oh yeah, if you want to run it, I've been using a keyboard shortcut to do Control Enter, but you can just click this play button as well. And then you can look at range array, and it'll be an array made from 1 to 10. And we'll see this when we look at our first classification model today. You can also change this value 1. That's the jump value. So you can change jump value to 2. And also one quick thing to notice, like I inputted 1 to 11, but the last number is not included. So it ended at 10. Now, if I jump by 2 and I run that, I'm going to see that I'm jumping by 2s in my arrange array as well. Okay. So now we can get started with the next main library we're going to need before we do our first machine learning project, which is pandas. So pandas is a data frame management library in Python, and we'll be using it to load in data and manipulate the data as well. So we can use this key function called .readCS functions to actually work with it. So NumPy, we can say import pandas as PD. And again, the PD is convention, and it's also just more efficient in terms of the writing. So we can go ahead and do that, and then we can load in the data frame. So I think the first thing, once you guys have got to this point, I want you guys to click add data on the side and search for diabetes dataset. And we're going to be writing a algorithm that can determine, based on certain factors, if a patient has diabetes or not on our first project. So you can click add, and it will add it to your workspace. So you'll see on the input, you'll see this diabetes dataset folder, and then inside is diabetes.csv. I'll give everyone a second to do that, but for those who have caught up with me already, you can kind of hover over the .csv file, and then on the right-hand side, there's going to be this copy file path button. So you can click on that, and I want you guys to just store that path in a path string variable. So path equals, and then just store the path as a string. Yeah, one thing you have to remember is that the order of these kernels does matter, and you do have to run each of these. So if you write something and you move on to a new box, and then you try to do something that's dependent on the previous one, it won't work. So because that code hasn't been run yet. So I'll probably just keep it one. Okay, so if everyone is done with that, I'm going to go ahead and load in the data frame. So what we can do is say data frame, or df, is equal to pandas, which we have left short form as pd, .read csv is the inbuilt function as part of that framework. And then we can pass in our path. So what that does is it goes to this CSV file, and it's now read it in as a pandas data frame. So we can make a new code block and go ahead and look at what does our data frame look like. So if I just type in df and run it, I'm going to see this table. So I've got all the input parameters: pregnancies, glucose, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, age, along with the outcome, which is the final outcome. So 1 is going to be positive for diabetes and 0 is going to be negative for diabetes. And then that will kind of be our output value or our Y value. And these are going to be all our input values or parameters. So if we actually look back all the way to when we were talking about the definition of what is machine learning, we talked about how it was a function with weights and parameters. So now in this case, in this example case, we had 3 parameters and 3 weights. So for this problem, we have 8 parameters, and each of these will have weights to basically correlate to how important are each of these factors when determining the outcome. So now what we're going to do is we're going to actually set our x and y variables. And there's a lot of nice functions in pandas to do that. So I'll go over some of these first, and then we'll use one of them for our application. So you can grab a certain column by doing data frame, and then in square brackets, you put the name of the column. So in here, in our case, these were the column names, right? And basically, it's similar to like accessing a dictionary with a key. It'll give you all the values in that column. And then if you want to get multiple columns, let's say I wanted to grab the age column and the whatever diabetes pedigree function column, I can add a comma and have a double braces. And to make a new column, I can put this and then a new column name in here and then set it to something. And then we can briefly go over conditional filtering. I guess just for testing purposes, we can say the age is equal to data frame of age. And if we look at the age now, we're going to see that it has all the age values. So we have 50, then 31, then 32, just like we do here. And then if I want to, do conditional filtering, which is basically filtering the data frame based on column parameters. So if I wanted to create a data frame that only held the data of people that were over a certain age, let's say they were over 30 or something, right? I can say, use this exact code. So I can say bool array equals the data frame total sales over 40. So if I say age over 30 is equal to data frame of age over 30, then that's going to contain the people over 30. So I was going to say true or false for now, right? Because the ones that are over 30 are true, and the ones that are not over 30 are going to be false. So now what we can do is actually get into our first machine learning algorithm. So if you guys want, you can make a new notebook because this was more of experimentation. I'm just going to keep going on the same one, but you can do either way. It doesn't really matter. So we're going to be making one of the most simple machine learning algorithms for today, which is the k-nearest neighbors classifier. So how this works is you have parameters. So in this case, there's only 2 parameters. And think about if there was like an axis right here, okay? And you plotted each of these points with a certain class. So the blue ones are a class which have certain properties, and the red ones are a class which have a certain property. And the green point is a new point that the model has to predict on. So what the k-nearest neighbors classifier does is it looks at its relative position to the other points in the data set. Now in this case, there's only 2 parameters, so they graphed it like this. But ours would actually have 8 parameters. So we can actually visualize what that would look like, an 8-dimensional graph. But it's a conceptual thing where there's an 8-dimensional graph and they all have distances. So what a k-nearest neighbor classifier does is it looks at the k-nearest neighbors and determines what class it should belong to. So if we say k-nearest neighbors, if we say the neighbors are 3 neighbors, then if we look at the green point, its 3 closest neighbors are 2 red and 1 blue, right? So it has a voting system and the majority is red. So if we were to look at 3 neighbors, we would give the classification of green as a red triangle. But if we were to look at 5 neighbors, we would have 2 red and 3 blue. So we would have a majority of blue, and this new point would be classified as a blue square. So what we're going to do in our code, which you'll see, is basically figure out the optimal number of neighbors for our program as well. So the first thing we're going to do is import NumPy as NP and import pandas as PB again. You don't need to do this if you're doing it on the same notebook, but for those who did switch over to a new notebook, you can do that. Someone got an error message. Let me look at that. Okay, yeah, I think Ethan helped out there. Okay, so once you have, oh, someone else had another error, 1 second. Yeah, so you need to just, Uganya, sorry if I butchered your name, but you just gotta make sure you run the pandas cell before running the other ones. Okay, so coming back here, go ahead and import those things, and then I'm going to re-import the data set as well, just in case people didn't do it. People made a new notebook, so we're going to say data frame equals read pd.read csv, and then this time instead of making it a string, I'm just going to directly pass in the string, but it works either way. So we have the data frame now. We can go ahead and look at the data frame, and we have the table just like so. So now we're going to set some actual x and y values. Just like I said, it's a math function. So we're going to have the input and we're going to have the output. So in our case, the output is going to be the outcome. So what we can say is y is equal to data frame, and then we're going to grab only the values of outcome like this. So if we take a look at what y looks like now, we're going to see that it's a row of this data frame with the exact same outcome values, just like this. And then for the x values, what we're going to do is use something new that we haven't looked at yet, but it's called the drop function. So we're going to do data frame dot drop like this, and then we're going to say drop the outcome. We want everything besides the outcome as the inputs, right? So we're going to say drop outcomes, and we're going to say axis equals columns. And what that does is we're saying we're dropping the outcome thing from the columns instead of the rows, because the rows are numerical. When we do that, we can look at x now, and x is everything besides outcomes. So now we have y, which is the outcomes, and x, which is all the input parameters, right? So now, one thing that we need to do, going back to the concept of, overfitting and underfitting, right? We want to have it generalize to new data. So the only way we can evaluate if it's working, if it works with generalized data, is if we have a separate testing set which the machine learning model has not seen. Because if we just give the model all the data, it might as well just memorize it and get all of our tests right. So we're going to keep it separate. I'm seeing another. Oh, yeah. So, Sophie, you have to actually run the cells. So you see like the little triangle there? You have to click that to run the cell, or you can click Control Enter for that. Yeah. Thank you, Robert. Okay. So now that we have that set up, we're going to go ahead and basically split it into the training and testing set. So you'll see what I'm talking about in a second. This is a bit of a nasty import, but we need to do it. So it's from sklearn dot, I think it's model selection, import train test split. So train test split is this great inbuilt function as part of sklearn, which is the machine learning framework we're going to be using. It's also known as scikit-learn, is what I called it in all the slides. It's basically this beginner framework that's really, really nice, and it has a lot of inbuilt functionalities, including train test split. So what we're going to do is we're going to set, what the train test split will do is it'll return us with 4 variables, our xtrain, xtest, ytrain, and ytest values. So we'll train our model with the xtrain and ytrain, and then at the very end, we'll evaluate the performance of our model on new data, which is the xtest and the ytest. So we'll say xtrain, xtest, ytrain, ytest is equal to train test split of x and y. So x and y, if you recall, are these data things, or are these data sets we made, of the x being all the parameters and the y being all this, and we're going to split it. And then we have to just specify a test size. So we're going to say test size equals 0.2, which is 20%. And then finally, just so we have some different results, we can say shuffle equals true. And that'll basically shuffle the data before splitting it up. So if we do that, we have our groups. And then what we're going to do, these are actually, if we look at the type, it's not going to work. It's going to throw an error. But if I go ahead and run this, you're going to see that the type of this is going to say data frame object has no attributed type. And this is because the xtrain right now is actually a data frame object. It's not a array or Python type. So what we're going to do is we're going to set it to a NumPy array. So what we can do is xtrain is equal to NumPy dot array or as array. We can use as array, or let's keep it simple. NumPy dot array, and then you can just pass in the same thing. So xtrain is now the NumPy array of itself, and just do that for all 4 of the variables. And I'll give everyone a second to catch up and then drop any clarifications. I know this is a bit, we haven't seen this type of code just yet. So if you guys have any questions, just please drop them in the chat and one of the TAs or me can get into it. Oh, yeah, for sure. I'm going to scroll back for just a second because I think someone missed it. But what I can actually do is probably delete this cell because this is not important. And then you guys can look at this. Yeah. Yeah, looks like someone's getting here. Did you make sure? Oh, yeah. So, I think that's different than what I have, by the way. I have diabetes.csv. So I think my path, Kevin or Kexon, is a bit different. It's diabetes.csv. So you might have inputted a different data set, and that might be why there's a problem. Yeah, but one thing you guys are going to have to do is make sure you add the data before. You can't run that string before you add the data. So what I had done earlier was I had clicked add data, and then I searched up, it's in my recommended, but if you search up diabetes data set, you'll be able to find it. And then I'm defining df, but it keeps saying undefined. Oh yeah, so same thing for you, Javier. You've got to just run the code. So to run the code, you have to go back and click like the run button. Like the little what is it? The little play button. I might be moving a bit fast. Let me please, like, anyone feel free to like speak up, unmute, put a message in the chat, and like ask me to go back to anything, clarify. Do we have time? Anyone want me to go back besides? Oh, I think someone said, yeah, okay. Jog, is that good? Okay, if anyone's not ready, please put it in the chat, or wants me to go back, please put it in the chat, or you can DM me. Otherwise, I'm gonna move on to the next step. All right. Okay, not ready yet. Sounds good. Wait. Okay. Thank you, guys. Okay, so I'll give it maybe like one more minute, and if anyone wants me to go back somewhere, just please let me know. Okay, I'm gonna delete some of these cells that are just for like demonstration purposes, so you guys get the idea of what's the actual required cells. Okay, so what we're gonna do now is we are gonna actually start to do our training process. Actually, yeah, Javier, just make sure. Just make sure you're running the cells. They don't look like they've been ran yet, so you have to hover towards the left side. Okay, good. And then what you guys are gonna do is basically set up this thing. So the first thing we're gonna do is actually use the numpy.arrange function to try a bunch of neighbors. So like we were saying, right, different neighbor counts yield different results. So we want to find the optimal one. So for our case, we're going to make a neighbors array, which is a range array. from 1 to 51. And what that'll actually do is, once you run that, what that'll do is if you actually take a look at it, you don't have to, whenever I'm saying like take a look and running it, feel free to do this as well, but it's not actually impacting the program itself. It's just kind of for us to look at it. And that's the advantage of notebooks. You can kind of just take a look at stuff and see how stuff is going. So I'm just going to look at the neighbors array and I'm going to see, okay, so I have 1 to 50 because I went 51. So it always goes one less. So I'm seeing, okay, so I'm going to experiment with anywhere from 1 to 50 neighbors and figure out what the optimal number of neighbors for this problem is, okay? And then I'm also going to make a blank array. So what this is called is, I'm going to call it test accuracy. And what this is going to be a empty NumPy array with, what is it? With the length of the neighbors array. And what that's going to do is it's going to allow us to later on fill this up with the corresponding accuracies of all of these so we can determine what the best number of neighbors is. Okay. And if anyone has questions about that part, because I know that's kind of conceptual, drop them in the chat if you want me to repeat anything. Okay. So now what we're going to do is actually do our training procedure, which is going to be like a for loop. So it's going to be, we're going to loop through each of these 50 different types of parameters. So we're going to do for I, comma, k in enumerate, and I'll explain what this does in a second, enumerate neighbors. And then we're going to just print I and k for now. So you guys don't have to do this with me. I'm just going to kind of show you what this enumerate for loop does, and then we'll get to the actual code in a second. So you can see like what this is doing is, so the first I value is a 0, then it's like every other value, right? So first one's a 0, then it's a 1, then it's a 2, then it's a 3. So that's literally just the index. Like in a regular for loop, if I were to do for I in range, it's like that. And then the k value is actually the thing at that position. So it's kind of like combining both the for I in neighbors and for I in range length neighbors into one array, or into one loop, sorry. I think we have a message in the red chat. Let me see what's going on with Caitlin's code real quick. Have you ran all of your code cells, Caitlin? Try that. Okay, so here what we're gonna do is basically try a bunch of different neighbors. So we're gonna say we're gonna initialize our first model. So actually for that we're gonna need a new import. So we're gonna do from sklearn dot neighbors. So again, sklearn is the scikit-learn. We're gonna say from sklearn dot neighbors import a neighbors classifier, which is gonna be the KNN model basically. Okay. And then we're going to make an instance of it, with each of the different neighbor counts. So each time we're going to say KNN equals k neighbors classifier with the number of neighbors equal to k. So remember, if you recall, k is the actual value from our neighbors array. So the first time it's 1, then 2, then 3, whatever. And it goes all the way to 50, right? So we're going to do all the 50 different types of trying neighbors. So the first time we'll just look at one neighbor. So in this instance, we would say, okay, it's red. And the second time we'll say 2, okay, it's red. 3, red. But then when we get to 4 and 5, we can get a majority of the blue class. And we're going to figure out which kind of neighbor count is giving us the highest accuracy in classifying diabetes. So once we have this, we're going to use the training function, which is knn.fit. And in fitting, we're going to have to pass in our X-train data set and our Y-train data set. And then that'll basically train the model that we just initialized on the training data that we previously established. And then what we're going to do after that is basically append the accuracy to this test accuracy array we made. So we're going to say test accuracy of I. So if you remember, I is the actual index. So the first time it's the 0th index and the first index, whatever, right? So we're going to take that previously empty array and fill that position with the accuracy of this model that we made with this many neighbors. So it'll be knn.score, which is the accuracy function. And then we're going to pass in the testing values, so x test and y test. So now what this kind of whole code block is doing is it's first importing the library we need for the model, and then we're looping through the neighbors with both the index and the item. Then we're initializing, or we're making a instance of the k-neighbors classifier with the number of neighbors that the model uses being the value from this array we made earlier. And then we're fitting or training the model with our training data. So they actually have this function inbuilt, which will use algorithms to figure that out. And then it will evaluate the performance of the model that was just trained on the testing set and save that value to test accuracy position. So if we run that, it's going to take a second, and now we've trained for all 50. We've found the values. So now we're going to actually use a visualization library to figure out how this works. So, or figure out what the best accuracy is. So we're going to, from matplotlib.pyplot, or sorry, import matplotlib as PLT. And this matplotlib is basically this massive like visualization software in Python, which helps a lot in terms of making graphs and plots. And we're just going to import it as PLT instead of having to type matplotlib.pyplot every time. So we're going to do plt.plot, and we're going to plot the test accuracy. And then we can just add some labels. That by itself should work, but what we're going to do is we're just going to add some labels for clarity. So we'll say plt.xlabel is the number of neighbors, and then plt.ylabel is the accuracy, and plt.title is the the accuracy versus the number of neighbors. And we're going to run that, and we're going to see that we have a this kind of graph where we're seeing that right here is kind of where the accuracy peaked at around 73-ish%. We saw the highest accuracy with our KNN classifier. So we're going to create a final KNN, which is called, KNN final. And then we're going to set it to another k neighbors classifier. Also, yeah, quick note. So we did shuffle. So some of you guys might get better results than me. Some of you guys might get worse results to me. So please analyze your own graph. Don't just copy the number of neighbors I'm doing. For me, I saw the highest accuracy at around 35 neighbors, 34 neighbors. So just observe your graph, see where the maximum point is, and then in your k-neighbors classifier, put number of neighbors is equal to whatever the optimal one you had. So I think for me, it was around 34. So I'm just going to write that. And I'm going to train my final model. So KNN final.fit with training data, and KNN final.score with the testing data. And I'm going to see, okay, so my optimal accuracy was 73. Well, I'll multiply by 100 just so we can see the percentage clearly. So I got 73.37%, or 0.37%. So once everyone has, looked at their graph of what they received, and then, chosen the maximum accuracy and, done this final part, just go ahead and drop whatever accuracy you received with your KNN classifier in whatever team chat you're in. And yeah, I think we should have some quite varied results. So let's see kind of who got the best. And also, we have about 10 minutes to spare. So if anyone wants me to go back, clarify, it's completely open. You guys feel free to unmute or, type your message in the chat and just at me, and I can help out wherever. And if you want to, if you're having a big problem with your code or something, I can have you guys share your screen as well and kind of guide you through it there. Can you share the code? Yeah, for sure. I'll share the notebook after this. Yeah, no problem. And I will share the code. I'll download the notebook and share it. It'll be a .ipnb.ipy notebook file. and then you guys can open it up on Kaggle probably, or maybe I can share. Yeah, public. Okay, nice. Yeah, so I'll go ahead and share that right now in the Discord, actually, in the CS1 resources. Um, and then if you guys have any questions, you can always reach out to me on DM or on one of the class homework help chats. Just add me and I'll come help out for sure. Can you please go back where test act is defined, please? Yeah, for sure. So it's defined like this. So what this does is it creates an empty numpy array, which is you have to define the size when you're making an empty array in numpy. So it's numpy.empty, and then you're putting I'm putting the length of the neighbors. So I want one test accuracy corresponding to each neighbor. Let me know if you need anything else, Robert. Yeah. And if anyone has got all the way through and done all the code and been able to keep up, just share whatever that final accuracy you got is. And if you haven't, then just drop a message in the chat or something, and I can help you get caught up. I think this is where I might have lost some people, so I'll leave it here for now. Have the same problem. Oh, okay, let me see this. From what I'm seeing on your code, Caitlin, it doesn't look like the cell above the one that's giving you the error is ran yet. It doesn't have like the thing next to it. If you look at the other ones, it has the number next to it. Yours says like 114 or whatever, which says which was the run number. But on that one above, it doesn't have the run number. So I think you might need to rerun. Yeah, you can press run all. Just start from the top, yeah. Keep getting error message again. Human testing is fine. Okay. I get this error message too. Oh yeah, so you have to use square brackets there on that one, Robert. Not able to open the link. Share public. Oh, I have to save a version. Okay. Yeah, I got it. I think I should save it first. Yeah, it'll take a minute, but I'll try to have it up after class because I think it'll take a second to run everything again. And I think that should do the trick. Let me go back and modify that link. Yeah, that's weird. Can you show the screenshot of the top code, the one above, and that one more time? I want to see because everything looks good from what I'm seeing. Can you please go up a bit? I missed a couple of cells above the y test equals numpy. Yeah, for sure. I think that. Oh, wait, is that the error too, Caitlin? Because that's just like a warning. If the red box is what you're talking about, that's just a warning. Is the error on that one or the X train 1. Kexon, is that enough, by the way? Up. Okay, cool. Okay, yeah, Caitlin, the red block is no problem. Kevin, for the second error, it's numpy dot arrange, not numpy dot array. It's neighbors equals numpy dot arrange, 1 to 51, and then the one above, I'm gonna need to see the block above that one too to tell you. Excellent, sorry. Yeah, so it looks like the block above isn't ran. So go ahead and run that the code block above that one, and then try rerunning it, and it should be fine. Okay, cool. So it looks like Sophie went all the way through, and yeah, that seems pretty close to what I got. I think 75. I think yeah. Oh, this looks like, so I just reran it. Looks like it got higher. Oh, this is a different one. Where is it? Yeah, here it is. Okay. Yeah, so it looks like cool. 75 is pretty good, and then looks like William also finished 70. Yeah, so there's gonna be some varying accuracy. Still an error. No module name sklearn dot. Oh, it's sklearn dot model underscore selection. And then, yeah. Okay, if you guys don't have any more questions, feel free to leave. I think we've got the material down. For those who do have questions or haven't quite finished, just hang around if you want, and I can like help you through it one-on-one. Yeah, that's what you did. I think what he meant was. Okay, yeah. Robert, do you want to share your screen by any chance?